In this lecture, we will discuss about the concept of model selection. We give you the aspects of selecting a good model, and we're going to see that not only the quality of the model should be considered, but must be other point of view as well. And that concept is very relevant to the famous bias and variance dilemma, or the bias and variance trade-off. The main points of today is to introduce the set of model selection scores. All right, these are quantitative criterion for you to pick a good model candidate. Suppose you have many choices. All right. The method of model selection also include the validation approach, cross-validation approach, but we will discuss about this in the next lecture, in the next video. Okay. In the model selection, the whole goal is to get a good model at a low cost. All right, like think about in the context of a linear regression. Suppose in your application you have n predictors, and n can be very huge. Like think about n is in the order of 1,000, 10,000, or sometimes it's 100,000, right? And of course, having a big model, the implication is you have to store or have the memory of, like you need to have a storage of the regression coefficients. So when n is huge, your model is more complex. All right. So here we would like to describe that when we look at the model, there are different three aspects. The first aspect is, of course, the quality. Okay, so this aspect can be explained by some measure, some indicator of the goodness of fit, for example, MSE or the log likelihood. Okay, we're going to show in the next slide that MSE, the mean square error of your model, actually consists of two terms, bias and variance contribution. The complex model has a small bias, which is a good thing, but I mean, on the other hand, it has a high variance, right? And this is in comparison to a simple model. So in the context of the linear regression, suppose like the candidate predictors included initially in the model is 10,000. So in comparison to another model, if you can come up with a reasoning that, oh, only maybe X3 and X5, these are only relevant, right? It can perform as well as the full model that use 10,000 predictors. Then this model is simple, is simpler model, all right? Of course, it's gonna have a higher bias, but on the other hand, it has a lower variance. So it's kind of a trade-off that we will discuss further. So the base model structure is therefore a trade-off between flexibilities. Flexibility can be obtained, can be explained from the goodness of fit of the model. Okay, and on the other hand, can be trade-off between parsimony, between the complexity of the model. The second aspect is to take a look at the price of the model. Okay, when we come up with the model, of course, in the estimation process, it also implies that we must require some numerical method, and we must think about, okay, what would be the computational complexity? All right. Think about neural network, right? And linear regression. I think everyone know by now that linear regression is simple model, neural network is a complex model. In terms of computational point of view, linear regression can be solved in no time. Like even though your variable is like 100,000. The numerical method is also a very mature technology. On the other hand, when you train the neural network, right? I mean, the variable is more than 10,000, and you need to train. You need like the time you spend in training the model is not I mean it's very significant. So in that case, okay, even though you know that the neural network is complex, right? Probably it fit the data better, but a trade-off is okay. The training process is time consuming. Okay. And the last aspect is once you had the model, what would be the intention or what would be the usage, all right? And in that different purposes of using the model, it also lead to different implementation, lead to different computations process, and that will bring you back to think about the model structure again. For example, if you're going to use your model for prediction, all right, everyone knows that for prediction, it means that this is the present time. You need to predict, values in the future. If you use model for the prediction, you need to archive historical values. And how far back you look at the history is up to your model structure. For example, in time series model, maybe your model will use the information in the past up to 2 steps behind, 2 steps previous. Okay, which means you need to store only 2 steps behind. But another model, it requires 100 steps previous. So this is different, right? Different model structure leads to different implementation, and it depends on the model usage. As we mentioned previously, that all the concepts in here, model selection, rely on the bias, variance, decomposition. We've seen this. Before. It basically expressed that when we talk about learning a statistical model, all of statistical models we present here, it just conceptually a function f, all right, that maps the predictor, the input variable, to the explained variable y. And this is the assumption that your data is generated in this way, data generating process, that your y has a relationship with f, okay, plus some corrupted noise. In your process of developing a model, you come up with a relationship f hat. F, the actual f, is something that unknown. You never know the true relationship between x and y. Okay. But you come up with f hat. For example, your f hat is the linear model, all right? It can be tree model, it can be neural network, etc. Right? So in this slide, it says that when you evaluate the performance of your model, you take a look at the actual y and the output of your model f hat at some x naught, all right, at some point of interest. Both variable y and x are treated as random. Okay, I would like to jump into the last equation. Okay, we can show that the MSE is decomposed into 3 terms. The first term is called irreducible error, and that is the noise covariance corrupted in the DGP. Which means if your data is is corrupted by noise, no matter how good your model is, all right, even though you can go to the neural network, like the very complex one, your MSE can never be made 0. There's going to be some positive, like threshold. This is the minimum. This is the best you can get, the mean square error. The second term is the bias of your model output, square. All right. The third term, this is the variance of your model output. All of the 3 terms, of course, these portions constitute the MSE. All the 3 terms are non-negative. Noise variance, bias square, variance. All right. we can show later that bias and variance cannot be made small at the same time. All right. If your model has lower bias, it's going to have higher variance. All right. Of course, a good model, you prefer to have low bias and you prefer to have low variance. This is for a good model, but I'm saying that these cannot happen altogether. All right. In order to show this, there's a proof here. I suggest you to read this proof. All right. That's not difficult. It's just basic derivation involving random variables. All right. So we can illustrate the decomposition of bias and variance in linear model. Suppose there are two scenarios, two candidate models, model M1, all right? Model M1, by this notation, it means that I use all the n predictors, okay? I use the matrix X that partition into n column this way. So here, it means that I use n predictors. For M2, the model 2, by this notation, it would mean that I add another predictor in the model. So in model M2, I use n plus 1 predictor. And of course, if I have n plus 1 predictor, there's going to be one more regression coefficient. I call it alpha. Okay. Which one refer to a complex model? Napat, M1 or M2?
M2.
M2. In this setting, M2 is more complex because it has one more variable, right? So M1 in this illustrate like a simpler model. We have 1, 2, 3 statements, but I'm not sure if I can, if I have like all the time to prove this. But the proof is in the slide. All right. Okay. The first one is M2. M2 will have lower MSE. Again, what is MSE again? MSE is mean square error. So if I need to be like very accurate about this term, so my MSE is basically what? The norm, all right? If I talk about M2, it's actually y minus z gamma norm square, all right? For the mean, it means that I need to normalize by the number of samples, all right? But the sum square error, so it's the 2 norm, all right? Okay, that is my MSE 2, all right? My MSE 1 would be the norm of y minus x beta square, all right? I'm saying that the MSE in predicting y, which is the mathematical formula here, okay, I'm saying that we can show MSE2 is lower than MSE1. The first one is very intuitive, right? Like, of course, we have a mathematical proof on this, but isn't that like very natural to understand that? Like you have for M2, you have more variable. Like think about, for example, if I have data point, right? M2 would be something like if I fit a polynomial model, for example, if I fit it to cubic polynomial, all right, and M1 would be the scenario that I fit it with a straight line. All right. So naturally, you would think that if I use cubic polynomial, if I use more complex model, I have more flexibility, right? I have more degree of freedoms. Those flexibilities refer to like you have more number of regression coefficients that allow you to have your model to be more flexible, and it can explain why better. When your model when your model can explain the response better, it will end up with having a lower MSE. Okay. This is the interpretation. As I said, a mathematical justification of all the claims are in the slide, all right? But I'm not sure if I have time on this. Okay, so I'm just give you the interpretation first. The second statement is that now you're looking at the quality of the model, like the ability to explain the response variable. But on the other hand, in bullet 2, I'm looking at another aspect. I'm looking at the estimator, the regression coefficients. Okay. In these two model, M1 the predictor is beta, right? But for M2, the model, the predictor, the regression coefficient gamma can be partitioned, like can be like it has two components. The first one is the same component as beta here, because this beta is multiplied with x with the same set of predictor as model 1. All right, but it has a second element alpha that correspond to x tilde. Okay. Now, so if I need to be like specific, let me put tilde here, because beta in gamma is not the same as beta in M1. Okay. The statement 2 says that the covariance of beta tilde, the portion, the first portion of the regression coefficient that associated with x, all right, covariance of beta tilde is bigger than covariance of beta in, this is for M2, this is for M1. Which means the interpretation of second one is that if you use more complex model, M2, your regression coefficient as an estimator, it is, of course, this is a random variable, but it is more, it is unreliable more than the estimator from a simpler model. Having bigger covariance is not a desirable property. All right. So for when we look at the second aspect, of course, we prefer M1 model. But if you look at the first aspect, you prefer M2 model. Let me put it this way. If you look at the first aspect, you prefer complex model. But if you look at the aspect 2, you prefer a simple model. Okay. And on the third bullet, the variance of y hat, all right, from M2, okay, is bigger than the variance of y hat from M1. Again, we need to be very specific about how we talk about the covariance and variance, all right? Variance of what quantity? Covariance of beta hat, this is the covariance of estimation error. Okay, because your beta is the estimator in your model. But of course, as we see before, when you do the prediction, the prediction of y, you use the equation y hat equal to the regressor matrix times regression coefficients beta hat, right? Which means that everything is random here. Your data is random. Your estimator beta hat is random. Of course, your predictor is also random. Everything is random, and that's why when we talk about its property, like we use some kind of moments in order to explain. For example, MSE, right? That's the mean of some square error. We use covariance to talk about these parameters, and with the same with the same reasoning, when we talk about y hat, all right, we look in the third aspect, we look at the variance of the prediction. Not only that, we take a look at the point estimate, right? Because the point estimate of y hat, it just gives us for practical purpose, like, oh, from this data set, your y hat is 2, and that's it, all right? But from statistical property point of view, if we characterize the variance, the third bullet suggests that if you use a more complex model, okay, it gives you more variance in the prediction. And that's when you take a look at this, of course, you might prefer a simple one. All right. And when you look at these all three properties all together, you see that all right, there is no like a single best choice. Choosing the complex model is not always the best thing to do because of the second the last two properties. All right, so I'm gonna skip the math, but I do believe that this is important, but the math behind here requires some linear algebra background. You need to know a lot of the matrices. All right, so I hope you read these slides, all right, in order to explain those three claims. All right. Okay. So in here we let me sum up again that when we after my part, like the lecture of this course, I'm gonna teach about regression model, right? That's a part of supervised learning. But after my lecture, that's Ajahn Vidyakon. He's gonna talk about classification. And after that, it's gonna be Ajahn Chanchai, who talks about supervised. All right, so there's gonna be, you're gonna see throughout the class, you're gonna see more and different kinds of model, but the principle that I'm explained here is conceptual, so it can be applied in many in other statistical models. In here, I put a sketch that where if you take a look at two aspects of models, on one hand, one direction, you look at flexibility. Flexibility means that like degree of freedom, like how the ability to adapt to explain the model. So if the flexibility is high, it means that the model explain why the response better. And flexibility always also proportional to model complexity. So in here, you see that linear model versus neural net. All right, neural net has more flexibility than linear model. There's going to be a generalized additive model. We probably you don't know yet, but I'm going to explain after this. All right, is this in the lecture? This is the lecture 10, all right? So generalized additive model is going to be more flexible, all right? We will talk about that definition soon. Restrictive linear model is a model where you assume that sum of the coefficient is 0, okay? For example, beta k is 0. So less strict linear model would be less flexible than the full linear model. Now, another aspect is if you're looking at interpretation of the model, the ability to interpret the model. As we see before in the linear regression, what happened when you run the regression, and of course you're looking at p-values of each coefficients. Suppose in the regression results is as the p-value corresponding to beta 1 is very high, right? So you have a reason evident to believe that beta 1 is 0. So what's the implication when some coefficient is 0? ธีรวัฒน์ อินทรวัฒนา
ครับ ฮัลโหลครับ
When some coefficient is 0 in the linear regression model, we can interpret that x1
that variable is not important or unrelated.
Right, x1 is not important. X1 is not, statistically significant to be included in the model. You see that with this in mind, your linear model, like there's because the structure of a model is linear, right? The structure linear here is simple. It's simple so that it allows us to interpret there's a level of interpretability that now you can say that the corresponding variable, the predictor, is significant or not significant. That's why the linear model, the ability to interpret the model is high in comparison to, for example, neural network. If someone used neural network before, you know that there's many layers, right? And the parameter of the models are what? Napat, what are the parameters of neural network? Napat?
Width and bias.
Weight and translation, and remember that these weight are associated with you know, each layer, right? One layer, you have this number of neurons, all right? And in practice, this is the number of parameters here in the neural net are huge, like more than 10,000, and no one ever want to look at the parameters like W and B, right? No one ever like have to print out these weight, the numbers. And even you have that, you cannot interpret anything. Like you cannot say, suppose if I have the weight of you know, 1, 3, for example, like if you have this number, it's less likely, it's difficult for us to say something, to infer something about these values. So neural network is a complex model, even though it has high flexibility, but it is difficult to interpret. All right. So people may have looked, may have looked at the flexibility all the times. Let's just focus on the MSE, focus on the, you know, performance in terms of MSE, MAE. But I'm saying here that that's not the only aspect you should keep in mind. All right. Okay. So in order to, this is what happened in practice, all right? When we train the model, when we develop a model, there's a training process, and there's a process of observing the test error. So we have a data set, all right? One for training the model, one is for testing. And once you have trained the model, you get theta hat, right? You evaluate the performance on the unseen. So the test data set will not be used in the training process. Okay. So we have this property characteristic that the training errors, the training error is the error that you actually you evaluate. So in the context of linear regression, suppose the training error. So suppose this is suppose this is the train data set. This is the test data set. So I use y tilde and x tilde, right? So the training error would be y minus x beta hat, all right? Where my beta hat is estimated from the training set. For the test error, that would be y tilde minus x tilde beta hat. Okay, the way you evaluate it. The training error is illustrated by the blue line. It's always decreasing in comparison to the complexity. Sometimes people use the term capacity of the model. So this blue curve is supported by the first claim I put here, that MSE of a complex model would be what? Would be less than MSE of a simpler model. So that's what you expect in the training error. Training error is always decreasing. Okay. The generalization error, which is the one evaluated on the test set, okay, often is not necessarily decreasing, but what you might observe in the actual experiment is that it has a U curve that at some point here it starts to rise again. Okay. This is what we typically say, that the degree to which that your generalization error start to rise again, that is the condition where you observe overfitting zone, which means you're using too complex model. Because in that sense, the model no longer adapt to the true characteristic of in the data, but rather adapt to something not significant. For example, the noise characteristic. Okay, in that phenomenon. Of course, the condition where your error is still too high, that is called underfitting zone. All right, you're using a too simple model in order to explain something that not simple. Okay, all right. Now we have some example of overfitting on the test error. This is the plot. All right. We have okay, hope you see in the screen. I don't want to zoom in because sometimes my screen freezes after zooming. On the left hand side is estimation data. All right, the data are the red points. Okay. On the right hand side, this is the test data. What you observe in the differences is, of course, the dot here. Are they the same pattern? Estimation and test. Panat, are they the same pattern? The pink one and the yellow one?
Not the same pattern, ครับ
Because why they're not the same pattern?
I think because of noise.
Yes, it's the noise characteristic. Hold on again. As I said, my screen freezes. The data, when we analyze these things, we believe that our data are generated from it's not on yet. Sorry, let's wait. What are you seeing on the screen? Is it my screen or what? Is it okay? Now it's here. Okay. We believe that all the data are generated in this way. Why? All right. It leads some relationship with the predictors plus some noise. All right. So of course, when you look at the pink dot, which are the data, the way that we say, oh, I try to find the trend. The trend itself is the same as I'm trying to find f hat to approximate f. All right. But of course, the pink and the yellow dot are not exactly the same because of the noise pattern that are random. Okay. Now, now we have three types of model. Okay, one is linear, quadratic, smoothing spline. All right. Between linear and quadratic polynomial, which one is more complex? Sukit.
Quadratic is more complex.
Quadratic is more complex. Smoothing spline, okay, we're gonna learn about that, but is about like smoothing spline is like you partition the function interval, and then you say that I will use polynomial in each interval. Okay, so this is my my model. This is fx, all right, which means in this interval of the values of x, I can use polynomial 1, polynomial 2, polynomial 3, all right. And the term smoothing, it means that there's some degree of your second derivative of fx that has to be, you know, has to be in some range, all right, in order to define the smoothness. Okay, so this is not smooth, right? Smooth. This is not smooth polynomial. So a smooth function also need to have some condition on the derivative, right? So smoothing spline, all right. With that brief definition, smoothing spline is going to be more complex than linear and quadratic. because you have more flexibility, right? In each interval of x, you allow it to be different descriptions. Okay, of course, you will see that on the left-hand side estimation data, the smoothing spline, which is the yellow, the orange curve, can fit better to the data points, right? And I mean, better than what? Better than the linear, right? Looking at the test data, what do you see? What do you see? Now it's not kind of a very clear cut that the smoothing spline can explain the pink data points on the test data set. All right. Now let's take a look at the plot of model complexity versus MSE. This is for polynomial model. The red one is the test MSE. The blue one is MSE. And of course, as we see again, MSE or the training error. All right. Sorry, I should use trend. All right. The trend MSE is always decreasing. But for the test, what do we see here? So it again kind of has the U shape. After the model complexity about 3, the test MSE start to rise again. And this is what we can see. Oh, that probably you're observing overfitting. Okay. And smoothing spline, all right, complexity of the smoothing spline actually characterized by this is what we call the number of knots. The knots are the transition points on the variable x. Okay, so the more knots, more number of knots, your model is more complex. And again, we observe the same thing. MSE always decreasing, but for test MSE, there's a degree of model complexity that the test errors start to increase. Okay, now it comes to the next question that, do we see overfitting all the times in all the data set, in all applications, in all types of models, in all the scenarios? Do we always see overfitting in general? Now let's take a look at these two illustrative examples. Now I explain in 2 cases. Okay, the first case is the actual f is nonlinear. Y equal fx plus noise. As I said, this is DTP. Okay, and we do the same. Now I'm gonna zoom in. Okay, we do the same. We the orange points are the data points, and we use a model from simple linear, right, to smoothing spline. This is supposed to be complex. All right, what do we see? In terms of fitting, which model fit worst? Trung.
Yes, Ajahn.
Yes.
Polynomial Ajahn.
Fit worst?
It was linear.
Linear, right?
Yes.
Polynomial and smoothing spline, you see some like subtle differences. Like the smoothing spline try to adapt to all these fluctuation in the data. Okay. Now let me move on to the right hand side. This is MSE. Okay. This is MSE. I think I plot only for polynomial, I guess. Okay. So this is the model complexity, basically the degree of the polynomial. What do you see here? You see that MSE decrease, MSE slightly increase, right? Let's observe this degree here. From second order to the third order, the test MSE actually increases, but by only a small amount. Okay. Now let's move to the second scenario. This is a scenario where the actual f is close to linear. The actual trend is linear. Okay, what do we see here? Again, in terms of the fitting, you see that the linear model itself also works fine. It can also, fit the trend, which is supposed to be linear. Again, the smoothing spline try to adapt to all these, variations in the data. Now let's take a look. Let's take a look at the test MSE versus the training. What would be the difference between the previous case and this case? If you look at the test MSE, all right. Again, at this about this order, second order, from second to third, your test MSE increases, but the amount your trace error increases, it seems to be more significant than the previous case. What's the conclusion here? The conclusion is that the overfitting phenomenon is more apparent to notice, is more apparent when the actual relationship between response and y is simple, f close to linear in this case. All right, does it intuitive, right? For example, when the relationship between response and y is actually nonlinear, like the dynamics of you can think of something like complex model, some biological system, something happening in your brain, all right? That the true relationship is supposed to be highly nonlinear. In that case, it would be, of course, better to use complex model structure in order to explain something that is already nonlinear. In that scenario, of course, the overfitting may not be like highly noticeable, as explained by this amount of the test error. On the other hand, if you're trying to explain something simple enough, simple or like already simple, for example, something that that it has a linear, like power is a constant times I, solar power, that is it can be explained linearly by solar irradiance. Okay, then in that case, I don't think that there's going to be more chance that you see overfitting phenomenon when you use a very high and complex model in order to explain something that is simple. That is the point of this slide, all right? Overfitting is not something that always happen, always occur. It depends on scenario, different scenario. It depends on the true characteristic of relationship. It depends on the model structure you choose. Okay. With that in mind, all right. With that in mind, what do we see? Of course, when we see overfitting, what does it suggest us? Napat. We should do nothing else. We see overfitting and then
we should reduce the model complexity.
Yeah, we should go back to take a look at the model structure and maybe use less number of parameters. For example, in terms of linear regression, maybe don't use all the predictors. Use only the relevant one. If you use neural network, maybe you don't need deep learning model. Maybe you don't need 20 layers. Maybe you need less, right? Because overfitting is something that basically says that you're using too much parameter in just order to gain something that's insignificant in the performance. And on the test error, it even says that, oh, your model is actually your model actually doesn't generalize well in the test set, right? and that's what overfitting suggests. So in this slide, so it means that, okay, then once we know that this information that, oh, there's going to be a trade-off between simple and complex, what can we do then? What criterion should we use in order to pick a good one? Today we introduce you these two model selection criterions. Okay, so model selection criterion relies on the parsimony principle that says you should pick the model that explains the response well, but you should pick the one that has smallest number of parameters. So if you have two models, both can be explained, both can explain the response like equally or about the same degree, why not choosing the one that's simpler, right? So the model selection criterion consists of two parts. The first one is the loss function, and that how you tell the quality of the model. But of course we're gonna take a look at the second concern, that is model complexity. Okay, so model selection score says that you should pick the model that the score is minimized. And in order to minimize this, of course, it's not it consists of two parts. These two parts are not low at the same time. Okay. Now, for example, when you have a simple model, all right, your loss function would be low, right? Sorry, no, not low. Loss function, for example, MSE, right? For example, if you use simple model, your loss function will be high, but yet the model complexity that, for example, can be determined by the number of parameters, right? Model complexity will be low, and if your model is complex, your loss function will be low, but the complexity is high. So that's why these two terms are trade-off, and we pick the one that sum of them is minimum. There's a commonly used scores in the literature of statistical model. The first three ones we call it log likelihood based model selection scores. AICc, corrected AICc and Bayesian information. In these log likelihood based scores, it requires the log likelihood function, right? So the log likelihood function basically the density function, the PDF function of the response variable, given that the predictor are these values and parameterized by a model parameter, and then take the log. All right, this is the log likelihood. Of course, so the better model, okay, the better model is the model that has higher log likelihood value. Okay, because this is the PDF, right? If the PDF is high, it means that the value of theta in the model you use, currently is the one that gives you the likelihood function that match well with this data set. And because the log function is increasing, if the PDF is high, the log is high. So that's why the higher the log likelihood, the better the model. Better in the sense that your model explains why better. Okay. So in all these three scores, they're going to use negative log likelihood. These refer to the loss function. Okay. All right. And the other term that represent model complexity, we use the parameter D in this slide. D is the effective number of parameters. So AICc use 2D, a corrected AICc has this extra term. Okay, these extra term also compensate. You see that there's going to be a function of n here, and that compensate for finite samples, which means when n is small. When n is small. For Bayesian information AICc, the effective number parameters or the term that refer to the model complexity degree also weighted, you know, or scaled by log n. Okay, so looking at this, all right, it says that, for example, if I use simple model in the context of linear regression, if I use only one predictor, right, one predictor, my loss function would be high. The negative log likelihood would be high, right? And then my D is what? If I use only one predictor, the effective number of parameters, my D is Sukit. If you have one predictor in a linear regression model, how many parameters in the model?
D1.
D equals 1, right? So your D is the second term is going to be low, right? So complex linear regression model that I suppose you have 100 predictors, of course. On the other hand, will have lower loss function, but D is 100. So D is going to be, the complexity term will be bigger. Again, how many number of predictors and which subset of predictors? So you're going to evaluate all the scenarios and evaluate the score and pick the model candidate that has the minimum AIC, AICc, or BAC. You pick your own, you decide the criterion you use and pick the model according to that. I'm gonna go over the Mallow CP. The Mallow CP is the criterion that actually associated with a linear regression model. All right. The parameter alpha here is the parameter that refer to model complexity. So it's a residual sum square that refer to loss function plus D, the number of parameters, all right, times the estimate of noise variance. So the second term refer to the complexity. Okay, adjusted R-square. This take a look at this formula. What is the conventional R-square? R-square is 1 minus RSS over TSS. All right, and for R-square, as you vary the model complexity, as you add more predictors, you see that the R-square, this is number of predictors, the R-square is always increasing. Adjusted R-square, now you have additional term, all right? You have additional term that kind of multiplicative to the residual sum square. This term has n minus d minus 1. So it basically means that the more predictor you pick, you add in the model, like if d is big, this denominator would be less, right? Would be less, and it will bring up this portion to be higher. Okay, everyone follow this? All right. When everything when this portion is higher, now adjusted R-square is gonna be less, right? Which means that's going to be a very appropriate value of D. In order to add more, in order to use more complex model, you need to make sure that the portion that the RSS is deducted should be worth, but because of adding more complexity, you penalize this term to be less. Okay. So in the plot of adjusted R-square, we will see it here. Okay, now I'm going to go over the examples. This is a problem of variable selection in linear regression. I would like to explain the data points y by using some basis functions, sine and cosine at different frequencies. Okay, so my k run from my k run from 1 to n, but my choice of n run from 1 to 20. Which means when n is 1, it means that I use only only single frequency. All right, I explain why on the basis of sine and cosine. If my n is 2, I use 4 terms. I use the sine and cosine at another frequencies as well. Of course, like the bigger the value of n, it means that more terms will be added up in y hat, which means I should explain y better, right? In this example, my actual y, my true relationship is the function of x times sine x plus noise, and that is the orange blue dots. Okay. Oh, sorry, is my actual y is actually plotted by the blue curve, all right, but because of the corrupted noise, the data points are the orange one, all right. So if I want to explain this relation, suppose that I don't know, in reality, in practice, you don't know that the actual function is x sine x, all right, but you assume that your model is trigonometric functions, okay, Fourier series in this example. The effective number parameters is 2n, right? Because at one frequency you have AK and BK, so you have n frequencies. So all the numbers, the number of all parameters is 2n. So when you compute, okay, suppose so you're gonna have n equals 1, n equals 2, n equals 20, all right, and then you're gonna have, for example, AIC1, AIC2, and AIC20, okay? Of course, what you can do is you can find the minimum one, and you subtract all score by the minimum one, right? When you subtract, of course, that's indicated by delta AIC, right? And then you're gonna pick the n, the value of n, that correspond to the scores that has the minimum, except the adjusted R-square. You pick adjusted R-square that has the maximum value. Now let's take a look at this plot. What do you see here? Different colors, different scores. You see that AIC peak the order about 14. BIC pick a lower model, all right? AICc also pick a lower model. Now this can be explained from AIC and BIC. AIC is the score is okay. Between AIC and BIC, the weight, all right, the scaling that penalize the model complexity for the AIC is a factor of 2, but for BIC is a factor of log n. What is n? Is the number of sample. So which score penalize more on the complexity if you look at this scaling parameter? Kilowatt. The term penalize means that if between, for example, if I have 10D and I have 1,000 times D, right? D is the number parameter, so it suggests the degree, the model complexity, right? you're trying to minimize the score. So if I have a factor of n, 10, and a factor of 1,000, with this choice, it means that I focus more on the complexity, right? I pay more attention. I care more about complexity. That's why I put so much weight in here.
Yes.
Yes.
Uh,
So with
so
that in mind, between AIC and BIC, which one has more weight on the complexity? What?
AIC.
Oh, log n and 2. Think
Um,
about log n. N is a number of samples. What? Like you have 1,000 sample. Log n, is it bigger than 2?
yeah. Yes, it's bigger than 2.
Yeah, so in general, like in practice, it's not hard to see that log n would be generally bigger than 2. So it means that BIC penalize more on the model complexity. And that gives us the supporting result, because this is how BIC shows the model. It shows 4 predictors. It prefers to pick a simpler model because BIC is more conservative on the side of model complexity. AIC on the other hand pick a more complex one. Okay. In the next graph, we see adjusted R-square and R-square. So what we have in here is that as we suggest previously, that the adjusted the R-square is always increasing as you varies the model complexity. Oh, sorry, I said R-square, all right, not adjusted. So R-square is not a good indicator for model selection, because choosing the model that has maximum R-square is always end up with the most complex one. All right. On the other hand, that's why we use adjusted R-square. Okay, and I think from this graph, probably here. So there's a model of order 15. Okay. And for the CP, mellow CP, again, it peaks around here. Oh, sorry, maybe I misread the graph. Okay, so you need to look at the number. And if we take a look at the MSE, now evaluate on the train and the test, you will see here that the MSE now you see that there's a kind of a knee curve here, that the test MSE is increase at this model complexity degree. So that suggests that you don't need to use higher order model like 10 or 12, 14. So these all information can help you select appropriate model. We have this again on the another example. Let me take a look. Now another example is on the time series model. This is autoregressive. It's described by this equation. All right. I hope you can verify yourself that in order to explain this model, that basically says you want to explain y at the current time by its own historical values. All right, y at step t minus 1, step t minus 2, and go to step t minus p, and that's what we call p order autoregressive. Okay. And the parameter you want to train estimate is A1, the coefficients here. Okay. And this model can be fitted by the least square formulation, linear regression. Please review. Okay. So now, of course, when you look at this model, the number parameter, or D, is of course P, the number of all AR parameters. Right. When you pick P to be very high, it means that you believe that you need to look further away in the past in order to explain the present time of YT response. So higher order RIR refer to a more complex model. In this data set, I try the meaning of Y is the unemployment rate. So again, we do the least square fitting, we compute the log likelihood, compare all the scores. Now we have data of samples, 245. In this example, I would like to illustrate two cases. The first one is I'm going to use up all the data, and on the other hand, on the second case, I use only half of them. On the right hand side, on the left hand side, okay. On the left hand side, what do we see? Let's notice that AIC, or the blue one, pick somewhere around here. For BIC, this is AIC, this is BIC, all right. And now on the right hand side of the curve, this is we have this another indicator that is called fit percent. Fit percent is the higher the better. It's actually the degree that explain why. All right. Now this is how you use only half of them, only half of the data. Now let me go back again. Okay, this is AICc. Now on the right hand side. On the right hand side, if you take a look, BIC also pick second order. Now AICc, okay, and AIC. So what would be the main distinction between these two cases is that I want you to observe the behavior of corrected AIC or AICc. On the left hand side, so in comparison between two cases, when you use less sample, AICc pick a lower or higher order. True. Yes. So, your voice is too low. Can you turn it on?
Lower
Yes.
order, Ajahn.
Lower order, right? So this is to point out that this is the intention of the corrected AIC. The formula is corrected in the sense that it takes into account the small sample scenario. So its behavior, the results of the results of the chosen model will be different. Okay, and in this case, in this example, we see that when the samples is less, AICc will pick a lower order in comparison to the case where the data are more. Okay. All right. Let me emphasize again that this is to illustrate how useful the model selection score can be in order to select a good candidate of the model. One common mistake in practice when I observe from students is they only look at the train MSE. They only look at the fit percent. These are not good for model selection purpose. It's not a good indicator where you compare one model in comparison to another model. This is just to observe the performance of your model of interest in one case. There's some interpretation about these scores in detail, more mathematically. I am not gonna go over that. All right. Yes, because time limitation constraint. But I would say this is important from theoretical point of view. You can read. If you have more questions, you can ask me in the class as well. All right, but it's just for at the moment the key concept is to understand the meaning of these scores The meaning that these scores also have a concern in two aspects, loss function and the complexity. And let me mention that all these scores, these are already, embedded in the results returned by the library. When you use linear regression command in any statistical software, already compute AIC, BIC, compute the Mallow CP, compute MSE, it compute adjusted R-square and R-square, everything. All right, it just your job is remain to the fact that you just need to be able to justify those scores, interpret those scores, and choose the model appropriately. Okay, I'm gonna stop now. And